Hi there, welcome to today's video. In today's video, we are going to implement a paper called Direct Speech-to-Speech Translation with Discrete Units. This is a paper that we have discussed in depth in one of my earlier videos, and today we are going to implement it. Good thing is that the authors of this paper have made their code public as part of the FairSeek library. So we'll try to follow the instructions that are provided in their GitHub repository. However, in order to implement the instructions that are given in the Direct Speech-to-Speech Translation with Discrete Units README file, there are some prerequisites that we must have. Since I've already done those steps, so I'll just list them out for you. All right, so what are the prerequisites? First thing is we need to create a Conda environment. This is just a good practice because we will be downloading or installing a lot of libraries, Python libraries. So it's just a neat way to organize those. We'll just create a new virtual environment. Okay, I will not go into the instructions of how to do that because there are a bunch of tutorials out there and it's pretty straightforward. So once we have that, the next thing is we need to install the FairSeek library. I have a video on my channel that goes into the details of how to install the FairSeek library. Please follow that video if you need help with installing this. And while we install this library, we'll also be installing the PyTorch and a bunch of other things. So once we have these two, now the third thing is we need, in order to train this model from scratch, we need to have the data set. So specifically, we need to have parallel speech data set. In my case, I'm interested in creating a language translation model, specifically speech-to-speech language translation model for a language called Punjabi, which is one of the Indian languages, to English. So language pair that I'm interested in is going from Punjabi to English. So as an example, that will be used, this pair will be used as an example throughout the video. So in my case, the data set that I want to have is Punjabi and English parallel speech dataset. So once we have these, then we are ready to go through rest of the steps here. So I'll just go through the steps and try to follow the steps. Actually, before I go there, I want to mention the dataset that I'm using. So in my case, the dataset that I'm using is a Fluor's dataset. This is a parallel speech dataset that contains parallel speech for about 102 languages. In my case, I extracted a subset, which is just English and Punjabi speech from this dataset, and that's what I'm using. So, I had to do a lot of pre-processing in order to get the parallel speech for these two languages. I will leave those details out because depending upon what data set you use, you will be doing different sort of pre-processing. So leaving those details out, I'll just mention that at the end of the data cleaning, what I had was the parallel speech data set for English and Punjabi language. Now, once I had those, now we can walk through the instructions that are given in the FairSeek library for direct speech-to-speech translation model. So by the way, we will be training a model from scratch for building a speech-to-speech translation model for the language pair that I mentioned before. All right, we'll start with here data preparation. Starting with number 1, it says prepare 2 folders, one for source audio, one for target audio. Source is the language that you want to translate, and target is the language that you want to translate to. In my case, I want to go from Punjabi to English. So source is Punjabi and target is English. So once we create these two folders, and then we need to create splits inside those folders. Splits are nothing but your test set, train set, dev set if you have it. And then inside those will be the data set that I downloaded from Fleurs, which it's basically just the raw audio files. And important thing is that these should be 16 hertz sampling rate for those audio files for this model to work. Let me show you how it looks like, just as an example. Okay, so in my case, this is my source audio, the folder, and this is my target audio, and inside this are my three splits: dev, test, and train, and inside each I have the raw audio files. So same thing, if I go to my target audio, it contains dev, test, and train, and if I go inside this, I have my raw audios of the target language, which in this case is English. Now, one very important thing that is not mentioned in the instructions but will haunt you if you don't do it is that the names of the files, these raw audio files, should match in the source and the target audio. What I mean by that is, so let's take an example from the source audio and let's take an example from the dev set. In this dev set, I have, as an example, I have this file called sample ID 1607_1. So this is one of these samples, right? Now the parallel speech for this particular sample in my target audio folder must have the same name. So let's try to search that. Let's try to verify that. So this, we want to make sure that a file with the same name exists in the target audio folder inside the dev folder. So here, and let's try to search the file. So we have a file with the same name. So very important. So inside the source audio and target audio, the files, the parallel speech data, inside these, the files should have the same names. Okay, so that's what we need to have before we proceed further. So this was the first step, to have the data set ready. Now, the second step is to prepare the target discrete units for speech to unit model training. Why is that important? If you remember, when we went through the paper, what this model does is it's trained to go from speech in one language to predict the discrete units in the target language. So when we want to train this model, we need to have these labels created. In this case, the labels are the discrete units for the target language. So let's spend some time in creating the discrete units for the target language, which is English. Okay, so what it says here is to prepare target discrete units for speech to unit translation model training, C generative spoken language for pre-trained K-means model checkpoints and stuff. So let's go there. Okay, so these are different models for going from speech to discrete units. In our case, we will use the Hubert model for creating the discrete units for the target language. So here we are going to download this pre-trained Hubert model, which is pre-trained on an English language, because this is what we want to use for our purposes. And then I will also be using a pre-trained quantization model. So in my case, I used a Hubert-based model trained on K-means cluster with 100 clusters. So I download this quantization model as well. So I download Hubert-based pre-trained model and quantization model from here to my machine. Then we can create the target discrete units. So according to this, there are two steps. The first is to learn k-means clustering. So in this case, I am not going to be doing this because I'm using a pre-trained model, this one. So I will skip this part and then I will directly go to the second step, which is to quantize using learned clusters. Now, if you don't want to use a pre-trained model, then you are free to create your own, learn your own k-means clustering model. It's up to you. For now, let's keep things simple and then just use the pre-trained models. So once I have downloaded this and this, then I want to run this. So let's look at what do we need in order to run this file called quantize with k-means. By the way, this quantize with k-means Python file is part of the FairSeek library, which we had to install before we even began this project. Okay, so what it needs is, it needs the feature type. In our case, we are using a Hubert feature. So this setup here, it can take one of these four features, logmel, CPC, Hubert, wave2, vac2. So we will just take the Hubert feature. So we'll say Hubert, and then here k-means model path. So this is where the pre-trained k-means model, the one that I downloaded from here, is going to be. In case you are training your own k-means clustering, then you would just take the output from here and give the path to that model. And then for the acoustic model, I'm using the Hubert base, which is here. So we'll just give it the path wherever that model is on our machine. And then layer. So in this case, it's asking which layer of the Hubert model do we want to extract the features from. So the original paper here, they say that they extracted it from the 6th layer, and then we'll just use the same for now. So we'll just say 6, and then we need something called a manifest, a path to the manifest file, which we haven't discussed yet, so I'll touch on that in a little bit. And then finally, we will specify where we want to store the output of this quantize with k-means after we run this file. So this, the output of this is basically the discrete units for the raw waveforms that we will be giving. And then extension is the extension of the audio files. In my case, all of the audio files are in the .wav format, so I'll just specify .wav. Okay, so we have pretty much everything that we need in order to run this quantize with k-means Python file. The only thing that we don't have is the manifest. So manifest is nothing, but it is a TSV file, which is tab separated file. So this TSV file, it contains the name of the audio files and the number of frames in each file, so as they show here. So what it will contain is, this is the path, absolute path, wherever the audio files are, and here it's the name of each of the audio file that is in a given folder, and then it will give us also, it will also have the number of frames in each of the files. So this is what a manifest looks like. So now, how do we create this manifest? For this, I actually have a video on my channel, which I will paste the link in the description below, and then we will know how to create a manifest file. So basically, what we need in order to create this manifest file is a folder that contains the raw audio files, and then we can create a manifest from those raw audio files. Again, I'll point you to the video that I already have that specifically focuses on how to create a manifest file. So I'll just show you what the output, what a manifest file looks like. So let's take an example. Okay, so here, let me show you an example of what the manifest file looks like. If I go inside my dev folder that contains the audio files for the target audio, here I have all of my audio files, and this is what a manifest would look like. So as we said before, it contains the header is just the absolute path, and then these are the names of all the audio files that are stored in this location, and the second column is nothing but the number of frames in each of the audio files. So this is what a manifest looks like. So that's what we need in order to create the Hubert units from discrete units using the Hubert model given the raw audio files. So let's, for the sake of proceeding further, let's say we do have a manifest file. So then we can just go ahead and run this command, and we will get the output. And one thing to note is that the output of this will be stored in the location that we specify, and according to the original setup, they are storing their output inside a target audio folder, and then basically whichever split we're working on, whether it's test, train, or dev, and the output is going to be a text file. Okay, so let me just show you in my case what these arguments were set to, just to show an example. Okay, so it's basically the same command, so don't get confused with what all this text is. So basically we do need to have the manifest file, which we just talked about. It's a TSV file for the data, and then we need to have the acoustic model, in this case the Hubert base, and then we also need to have the quantization model. In this case I'm using a pre-trained one which I downloaded from here. So once I have these three things, I am ready to create the discrete units for the target language by running this. Okay, so in my case, so one of the things you might want to take a note on is, before we run this file, quantize with k-means, you have to be inside the fairseek folder, wherever that fairseek folder was downloaded when we installed the fairseek library. So you have to be inside that, just to make things simple, because this examples and this is just a structure inside the fairseek library where this Python file is stored. Okay, and then other things are basically like we discussed. So feature type is Hubert, and then k-means model path is wherever my k-means model is stored, and the acoustic model path is wherever my Hubert model is stored, and then I specify layer 6, and then I specify the path wherever my manifest file is stored, and then finally I have I need to specify where I want the output to go, and here I am storing the output inside this folder target audio train, and then extension is WAV because all of my files are in the WAV format. Okay, so once we run this, so in this case I'm running it 3 times because I have three different sets: train, test, and dev. Command is the same, just the arguments would change a little bit depending on just where the files are stored and stuff, and where you want to store the output. So these are all the 3 same commands basically, with arguments adjusted. Okay, so once I run this, then I'm going to get a text file. Let's look at what that text file looks like. So text file is going to be stored in the target audio directory, and then I have the one for the dev, one for the test, one for the train set. So if I just open up the dev as an example, the text file is going to look like this. What this really is so this is the sample name of the audio file. So this is the audio file in English, and these are the discrete units for that audio file. And again, this is the another raw audio file name of that, and then these are the discrete units for that audio file. Same thing, this is another sample name, and then these are the discrete units for that audio file, and these discrete units are created using a Hilbert model. So that's what the output of running this looks like. So let's just go back and try to summarize what we just did. So we had originally we had the data, we had the parallel speech data for the target and the source language, and then we had to create a data manifest because we needed the data manifest to actually create the discrete units for the target language. Remember, the discrete units that we just created are only for that, we only need that for the target language. Why? Because this speech to unit translation model, it goes from the speech in the source language to discrete units in the target language. So that's why we only need to create this for the target language. In my case, that is English. All right, so we have done the steps that are mentioned here. Next is a formatting data. That means we now want to prepare speech-to-speech data for training the model. And here, as you can see, they have two sections. One is speech-to-unit translation, and then one is speech-to-spectrogram translation. We will not do this because this is if you want to go from speech in one language to spectrogram in the other language, but we are not going to do this. We're just going to focus on going from speech in one language to discrete unit in the target language. So we'll just do this. Let's run this, and then after we run this, then I will explain why we had to do this. So let's make sure we have everything that we need in order to run this prep speech to unit data script. So here they say the arguments that it takes is the source directory. This is the location on your machine that contains the source audio files. And remember, we created this folder in the beginning here, source audio and target audio. So these are the folders that we need to give the location to this argument source directory. Similarly, target directory would be wherever the folder target audio was is created. And then data split would be the splits that we have in the data. For example, whether it's train and test or train, dev and test, however many number of splits we have, we specify each split here. And then we need to specify the output. Where do we want to store the output of the script? So here, as you note, they are using a folder called data_root. This folder does not yet exist, so we will have to create this folder, and then once we have done that, then we can give the location of that folder to this argument, and then reduced unit, vocoder checkpoint, and vocoder config file. These two can be downloaded from here. So this is the vocoder checkpoint and vocoder config files. We can just download them and then give the location to wherever those files are downloaded to these arguments. All right, so let me show you an example of my setup again. We will need to be in the fairseek folder, just like in the previous step. This is the folder that is created when we first download the fairseek library. So once we have this, once we're inside this folder, then we can just run that command that we just saw. So here, As I said before, for the source directory, I just give it the location of the source audio folder, and then for the target directory, I give it the location of the target audio folder. And then in my case, the data split, I have 3 splits. So I specify train, dev, and test, and then I have the output going inside the data root folder, and my data root folder is located here. And then we use the reduced unit, and then for the vocoder, I specify the location where I downloaded the pre-trained vocoder, and also the vocoder config file where I downloaded that, the location to that. So after I run this, I'm going to get an output that consists of 4 different things. So I will have a config.yaml file, and I'll show you what that looks like. And then I have a TSV file for each of my splits: dev, test, and train. So let's go inside the data root folder here. This is where all of our outputs of this command that we just ran are. So let's go inside that folder and look at what the output looks like and what it is. Okay, so let's go inside the data root folder, which is right here. So as you can see, ignore the other things because we haven't talked about those yet. But if you notice, we have a config YAML file, and then we have the TSV file for each of the splits. Let's look at the TSV files first. So if we just look at the dev TSV file as an example, so as you can see, this TSV file, it has 4 columns. The first is the name of the audio file, and this is the source audio, by the way. So this is the audio file. It's the raw audio and stored inside the source audio folder, and this is the name of this file. You can see sample ID 1639_1 is just the name, and this is the actual path, and this is just the number of frames in that audio. And these 3 just are telling you everything about the audio files in the source language. And on the column here on the right is the discrete units for the target language. So let's pay a closer look to what it is. So remember, the model that we want to train, the translation model, we want to train it to go from the source language, the raw audio in the source language, and we want it to predict the discrete units in the target language. So in order for the model to learn how to go from the raw audio in the source language to discrete units in the target language, we'll first have to give it a training data, which means we want to, in this case we are doing supervised training, so we want to give it the label. So think of this as labels. So here we are preparing the data for training the speech to unit translation model. So here we are just saying for this audio in the source language, this is the discrete units for that parallel audio in the target language. So let's say my audio is in language Punjabi, and I'm asking ki hal hai. So let's say that's just an audio in Punjabi asking how are you. So for the English, I will have a parallel speech which is saying how are you. But because we are training the model to predict the discrete units, I want to give the discrete units as labels to train the model. So that's where we are mapping the raw audio in the source language to discrete units for the parallel speech in the target language. I hope this is clear. So this step was important because this is the data that we want to train the model with. Now let's just take a quick look at the config YAML file. And here, this is auto-generated. It just has some arguments. I won't go into the details. but it's really important that we understand what is inside this TSV file, and they all have the same thing, just for different splits. Okay, so now we have the data for training. Before we proceed with training, they have additional stuff here which says multitask data. So now you can go ahead and train the model with the data that we just looked at. You can give it a try, but the paper mentions that we get better results if we use multitask data. What we mean by that is, so rather than just training the model to go from speech in one language to discrete units in the other language, we also train it to learn other things, such as the words or letters or phonemes. So we are doing what we call is multitask learning. So again, you can just stop here and just use this data to start training your model and see what you get. But if you're interested to improve the results, then we do need to create this multitask data in order to get better results and then finally train the model. So we have this one more step to do before we actually start training the model. So let's look at how do we generate the multitask data. So here they say for generating this multitask data, it's up to us what kind of task we want to train it for. They've done several experiments as they show in the papers. For example, you can use target words, you can use source words, you can use target phonemes, you can use source phonemes. So you choose what task you want to use in multitask learning. In my case, I experimented with using the target words or target tokens. In my case, the target language is again English. So I use target words as a task that I want to use in the multitask learning. So we will define the task name, and then we need to create this folder. So inside the data root folder where we were just in, we will create another folder with the name, whatever the name of the task is that we choose. And then inside this, we will store the TSV files, one for train, one for test, one for dev, depending upon how many splits you have. Then, this is very important, as they say here. I'll show you an example and we will talk about what they mean when they say sample IDs should match with the sample IDs of the speech-to-speech data. So we'll talk about that in a little bit. So the format of the data should look like this. So you have a TSV file. The first column is the ID, which contains the ID of the audio that not just the audio, but if you have a transcript, but the sample ID. And then you have the second column, in this case target text. I'm using the target tokens, so I just call it target text, and then it contains the tokens for that particular sample. Again, I'll show you just an example in a minute. So for each multitask, so if you want to use more than one task, in my case I'm just using one additional task, but if you want to use more than one task, then you just have to repeat this. You have to create a folder with the task name and then prepare the TSV files and so on. So once we have created the TSV file, one additional thing that we need here is, as they say, for each multitask, prepare dictionary.txt. So here we just created the TSV files, but we also need a dictionary. And then I'll show you an example what that looks like. And once we have that, and then we will just create a config multitask.yaml file. Okay, so three things. Let's say we only want to use another task. So I will define the task name, and for that task name I will create a folder inside the data root, and for each of my splits I will create a TSV file in this format, And then for that task name, I also need to create a dictionary.txt file. And then finally, we will create a config file that looks like this. And here you will specify all the tasks that you have. In this case, I only have one task, so I will specify the task name here. And then I will specify where my dictionary is and where my data is. And that's pretty much it. So let's look at an example. So I will not go through like how to create a multitask data because that's a whole different thing. I'll just show an example of what my multitask data looks like. All right, so as they said, we need to be inside the data root. So I'm inside the data root and I create a folder for my task. In this case, the task is target word. So I create a folder called target word. Inside this, I need to have the TSV files for each of my splits. So let's inspect what a TSV file looks like. Okay, TSV file is as shown in their example there. So we have a ID, sample ID, and then we have in my case, I'm using target word. So that's why I split the transcript for that particular sample ID. I split that into tokens. So these are just the words or tokens. What they mean by when they say that the IDs, sample IDs should match with the sample IDs for the speech-to-speech data. So this name here, the name sample ID 1536_1 should match whatever the corresponding speech data is for this particular target text. Local authorities are, so it's very important, otherwise you will run into problems. So make sure that the sample IDs here match with the corresponding sample IDs in the speech-to-speech data. If you have further questions, just let me know. I will provide more examples in the comments if needed. And then, so once we have the TSV file, they all look the same. It's just they're for different splits. Again, sample IDs and target text. You have the tokens. Finally, I need a dictionary text file. Dictionary is nothing, but it's just all the different words that are in my vocabulary. And then I just have a word and then how many times that word appears. This is again another word, how many. So this is just what the dictionary format needs to look like. So we have all the ingredients that we need. The last thing is we need to create this source file. Sorry, the config_multitask YAML file. So let's look at what it looks like in my case. This is something you have to create manually. So again, let's compare it to what they have in here. All right, so in my case, I only have one task that I am working with. So it's my task name is target word. So, and for my decoder type, I'm using a transformer, and I specify where my dictionary is, I specify where my data is, and I specify encoder layer and loss weight. I just kept the same as here. So since I only have one task, I only have one item here, as opposed to they having 3 different items. All right, so now we have everything that we need for training. So we created, I'm just going to briefly go over what we have done so far before we proceed next. So what we have done so far is, first we just procured the training data, which was the parallel speech data for the source and the target languages. And then for the target language, we created the discrete units, because we want to go from speech, raw speech in the source language, to discrete units. So we created that. And then here what we did was we mapped the source language, the raw audio in the source language, to corresponding discrete units in the target language. So we did that mapping. And then additionally, we also created a multitask data. In this case, I was using target words. And then Once I have all that, now I'm ready for training the model. So I will mention and I will go through the details of training in the next video, because I think this video is getting a little bit longer. So I will go through the training process in the next video. So I hope to see you there. Thank you. Bye.